Hello to everyone. In Engineering Mathematics 1, I am going to discuss matrices. First, definition of matrices. A matrix is a rectangular array of numbers arranged in m horizontal rows and n vertical columns enclosed by a pair of brackets, that is m by n. Matrices are usually denoted by capital letters, that is capital A equal to, so this denotes m rows and this denotes n columns. The general form of matrix is capital A equal to Aij m by n, where I equal to 1 to m, j equal to 1 to n. Now matrix A equal to, so put I and j value, so first one A11, second one A12, then A13, last one A1m, A1n, that is first row and nth column. Now second row, so A21, A22, A23, etc. to A2n. Now third row A31, A32, A33, etc. to A3n. Similarly, the last 10 AM1, M row, AM2, AM3, etc. to AMN. So horizontals are denoted by rows and verticals are denoted by columns. So this is M by N matrix. Matrices are very useful in nuclear physics, aerodynamics and astronomy and electrical circuits. Matrix methods are very easy to write. Many computer application programs, especially in information technology, it's play a significant role in network theory, image processing and so on. Now, order of the matrix. The order of the matrix is denoted by its number of rows and columns. Here m rows and n columns. So the order of the matrix is m by n. Suppose I am taking first 3 terms. So A11, 12, 13, 21, 22, 23, 31, 32, 33. So here 3 rows and 3 columns. So the order of the matrix is 3 by 3. Suppose I am taking first 2. So here 2 rows, 3 columns. So order of the matrix is 2 by 3. Suppose I am taking this particular term. So first row, second row, third row. So 3 rows and 2 columns. So the order of the matrix is 3 by 2. Suppose this particular part means 2 rows, 2 columns. So the order of the matrix is 2 by 2. Now types of matrices. Here first one, row matrix. Second one, column matrix. And third one, square matrix. The first one, row matrix. A matrix having a singular row is called row matrix. For example, A equal to having a single row. So 1, 2, 3. So the order of the matrix is 1 row and 3 columns. The order of the matrix is 1 by 3. So this is the example for row matrix. Second one, column matrix. A matrix having a single column. So example the same elements 1, 2, 3 in a vertical line. This is horizontal, this is vertical. So the order of the matrix is here 3 rows, 1 column, then third one, square matrix. A matrix is said to be square matrix if its number of rows and number of columns are equal. For example, A equal to 1, 2, 3, 4. So here order of the matrix is 2 rows and 2 columns. So 2 by 2. Here M and N are equal. Number of rows and number of columns must be equal. Then only the given matrix is said to be square matrix. Suppose 1, 2, 3, 4, 5, 6. It's a matrix, but it's not a square matrix because the order of the matrix is 2 rows and 3 columns. Then fourth one, null matrix. Null matrix or zero matrix. Matrix is said to be null or zero if all the elements are 0. For example, A equal to 0, 0, 0, 0. That's all. This is example for null matrix. Now, fifth type, diagonal, scalar, seventh one, identity or unit matrix. Diagonal, scalar, identity. If the matrix is said to be diagonal or scalar or identity, first it should be a square matrix. The definition for diagonal matrix, a square matrix is said to be diagonal if all the elements except elements in the main diagonal are 0. For example, all the elements except elements in the main diagonal. For example, 3 by 3 matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. This is an example for 3 by 3 matrix. Now diagonal means all the elements, this particular part is called main diagonal elements. All the elements except elements in main diagonal. Elements are 0 means that matrix is said to be diagonal. That is, these two terms must be 0, then here. Yeah, that's all. This is an example for diagonal. Again I repeat, a matrix is said to be diagonal if all elements except elements in main diagonal elements are 0. Now next type, scalar matrix. The difference between diagonal and scalar is all the elements except elements in main diagonals. If the main diagonal elements are all are equal means that is the example for scalar. For example, the same here 1, 5, 9, 2, 2, 2, 0, 0, 0, 0, 0, 0. But the condition is your main diagonal elements are equal at the same time except 1. So it may be 2, 2, 2 or 3, 3, 3 or 9, 9, 9. So example for 3 by 3, if it is 2 by 2 means 2, 0, 0, 2. This is example for 2 by 2 matrix. Then 7th one, identity, the same, your main diagonal elements all are 1 means that is example for identity. The same definition. All elements are 0 except your main diagonal elements. So example for identity matrix is A equal to 1, 1, 1, 0, 0, 0, 0, 0, 0. This is the example for 3 by 3 matrix. 2 by 2 means 1, 0, 0, 1. Usually it is denoted by, so this is 3 by 3. So I 3. It is 2 by 2 means I 2, 1, 0, 0, 1. So this is example for 3 by 3, this is example for 2 by 2. or eighth one, upper triangular matrix. Ninth one, lower triangular matrix. Now, upper triangle and lower triangle, the same, it must be a square matrix. Now, example for upper triangle matrix, a matrix in which all the elements below the main diagonal elements are 0. For example, A equal to below the main diagonal elements. For example, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the example for 3 by 3. Now, upper triangle means in which all the elements below the main diagonal elements are 0. Here we know that the main diagonal elements are 1, 5, 9. So, below the main diagonal elements are 0 means it is example for upper triangle. So, that is these 3 elements are 0. That's all. Now, the next one, lower triangle, the same. Here, below the main diagonal elements are 0 means that is example for upper triangle. Now, lower triangle means above the main diagonal elements are 0. That is 1, 2, 3. These 3 elements are 0. Here 4, 5, 6. Above the main elements are 0 means that is example for lower triangle. Below the main elements are 0 means that is example for upper triangle matrix. Next one. Symmetric matrix, and last one, singular matrix. Now, symmetric, a square matrix. Here also symmetric and singular, it must be a square matrix. A square matrix is said to be symmetric when Aij equal to Aj. This is a condition for all I and j. For example, A equal to, the general form of 3 by 3 matrix is A11, A12, A13. Second one, A21, A22, A23. Third one, A31, A32, A33. So, first look at your main diagonal elements. Aij equal to Aji. Your first elements are I, your second elements are j. So, Ij, here this was same, these two are same. These two are same. So, you no need to bother about your main diagonal elements. Now, second one, A12, reverse one, A21. So, these two elements must be same. Similarly, A13, A31, A23, A32. So, these two, and this must be same. For example, 1, 2, 3. No need to bother about your main diagonal. Here 4 means here also must be 4. Here 5 means here also must be 5. So, now second one, here 6 means here also must be 6. So, this is an example for symmetric matrix. Now, last one, singular. Singular matrix. A square matrix is said to be singular if the determinant value of the matrix is 0. For example, A equal to 1, 2, 3, 4. This is 2 by 2 matrix. Now, the definition is if the determinant of the matrix, so this is not a determinant, this is a matrix. The determinant means it is denoted by 2 vertical lines instead of brackets. So, 1, 2, 3, 4. So, this is the determinant of the matrix. This is 2 by 2 determinant. Similarly, for 3 by 3 or 4 by 4. Matrix A equal to 1, 2, 3, 4. So, the determinant value of the matrix is 0 means, so the given matrix is singular. Now, I teach you how to find 2 by 2 determinant. Procedure, first multiply from up to down, next down to up. Up to down, 1 4s are 4, 3 2s are 6. Here symbol is first up to down, next down to up. whenever we are multiplying from down to up, you should include opposite sign. If it is plus means minus, minus means plus. Here plus into plus, plus, here also plus into plus, plus, so opposite sign minus. So the answer is minus 2. So this is not a singular matrix, because singular means your determinant value must be 0. So here also determinant A, here also determinant A. So now 1, 4, 2, 3. Here I am just replacing 3 by 2. Now 1 4s are 4, 2 2s are 4, plus into plus, plus, so opposite sign minus. So 4 minus 4, 0. So the determinant value is 0. So this matrix is said to be singular. Transpose of a matrix. Transpose of a matrix is a matrix obtained by interchanging its rows and columns. For example, A equal to 1, 2, 3, 4, 5, 6. The order of the matrix is 2 by 3. Now A transpose. Transpose of the matrix is denoted by A transpose. So interchanging its rows and columns. So it can be written as 1, 2, 3. So rows, here is coming columns 4, 5, 6. So interchanging its rows and columns. Here the order of the matrix is 3 by 2. See the difference? Here 2 by 3, it becomes 3 by 2. Now multiplication of matrices. Two matrices can be multiplied only when the number of columns in the first matrix is equal to number of rows in the second matrix. For example, matrix A equal to 1, 2, 3, 4. So the order of the matrix is 2 by 2. Matrix B equal to 4, 5, 6, 7, 8, 9. So the order of the matrix is 2 by 3. So the definition is number of columns in the first matrix 2, number of rows in the second matrix 2. If it is equal means we can multiply, otherwise we can't multiply. Here it is possible. So A into B, here 2 by 2, here 2 by 3. So matrix multiplication order becomes AB, which is equal to the remaining 2 into 3. It's cancelled. So order of the matrix of AB is 2 by 3. So matrix multiplication, first row, first column, then first row, second column, then first row, last column. Similarly, second row, first column, second row, second column, second row, last column. Now next one. Characteristic polynomial. The determinant A minus lambda I. The determinant A minus lambda I, here A is matrix, I is identity matrix, lambda is eigenvalue. The determinant A minus lambda I is expanded, will give a polynomial. So next one, characteristic equation. The determinant equal to 0. The determinant of A minus lambda I equal to 0 means that is characteristic equation. Now I give you one example for characteristic equation, how to find characteristic equation of the matrix. Now find the characteristic equation of the matrix A equal to 1, 2, 3, 4. So 2 by 2 matrix. Okay. So we can solve this problem by two methods. First method, a procedure, that is determinant of A minus lambda I equal to 0. Clear? So again I repeat, A is given matrix, I is identity matrix. Now A is given, determinant 1, 2, 3, 4 minus lambda I is identity matrix. So this is 2 by 2. So I2 1, 0, 0, 1. Determinant symbol equal to 0. Now multiply inside the bracket means lambda 0, 0, lambda. Then subtract the corresponding elements. This becomes 1 minus lambda. Second one 2 minus 0. Third one 3 minus lambda into 0, 0. So 3. The last one 4 minus lambda equal to 0. So we know that 2 minus 0 equal to 2. Now this is 2 by 2 determinant. So already we know that how to find the value of 2 by 2 determinant. That is, first multiply from up to down, then down to up. Whenever we are multiply from down to up, we should include opposite sign. So first up to down, 1 minus lambda into 4 minus lambda. Next down to up, 3 2s are 6, here symbol is plus into plus, plus, so opposite sign minus, 6 equal to 0. Now here multiplication, first into first term, first into second term, second into first term, second into second term. Now 1 4s are 4, 1 into lambda, here plus, here minus, plus into minus, minus, that is minus lambda. Then second into first, so minus 4 lambda. Then second into second, minus into minus, that is plus, so plus lambda square minus 6 equal to 0. Rearrange the equation. So first lambda square minus 4 lambda minus lambda, here coefficient is 1, so minus 5 lambda, 4 minus 6, so minus 2 equal to 0. So this is the characteristic equation of the given matrix. So this is 2 by 2, 2 by 2 means square, lambda square. So if it is 3 by 3 matrices means here the answers must, first term must be cube, lambda cube. This is the example for 2 by 2 matrix. Now second method. Given matrix is 1, 2, 3, 4. The same. The answer is lambda square minus 5 lambda minus 2. Because already we know there is this problem by first method, minus 2. Now method 2. Method 2 is formula method. That is, a formula is lambda square minus S1 lambda plus S2 equal to 0. Here S1 and S2 are constants. So instead of S1 and S2, you can use C1, C2 like that. Now 2 by 2 matrix, so your formula start by lambda square. Suppose 3 by 3 matrix means your formula is lambda cube. Next one minus, the symbols are alternative, plus minus plus minus. So minus S1 lambda square, just reduce the power, degree, cube, next one square, so next one here minus, so next symbol plus, here you use S1, so next one S2, so lambda square means lambda, so last one minus S3. This is a formula for 3 by 3 matrix. Now 2 by 2, lambda square minus S1 lambda plus S2. Now I tell you how to find S1 and S2. S1 is nothing but sum of That's all. S1 is sum of the main diagonal elements. S2 is determinant of A. So sum of main diagonal elements. I hope everyone know the main diagonal elements. Here our main diagonal elements are 1 and 4. So sum of main diagonal elements, that is 1 plus 4 equal to 5. Now second one, determinant of A. So determinant of A, that is 1, 2, 3, 4. Determinant. So this is as usual multiplication, first up to down, then down to up. So 4 minus 6 and 3 is minus 2. That's all. Sub these values into your formula. So answer lambda square minus S1. S1 and 3 is 5. So 5 lambda plus S2. So S2 answer is minus 2 equal to 0. So the same answer. See, the same. So compared to method 1, method 2 is easy because this is 2 by 2 matrix. When we are going for 3 by 3, compared to method 1, method 2 is easy.